And I also put material for next week. We have this week and next week. The readings. Yeah. This week, next week. It doesn't open. Okay. Well. I'm sorry. The material doesn't open. Let's not do it. Oh, maybe I didn't. Publish it. Or 18. Oh, maybe I didn't publish the whole module. What does this do? Publish. Sorry, I published the things underneath, but I didn't publish any. How does it work? Okay, so I should have emailed everybody on the coast. Is that right? Good. All right, so I'm going to pass these out to these people here real quick. Oh, really? Because I was sending you. Who knows? I can go over that later. Okay, so we'll go over the exam, and I will talk about the question and what the appropriate answer was, and if I did get partial credit, I'll talk about that. The number at the top of the page is how many you missed. Technically, the exam's out of 50. They changed the scale a little bit. Your grade is what you got on midterm for the course. Midterm is your grade for the rating. So I curved it, or whatever you want to call it. Adjusted the grades. And there's not a whole lot of without getting too specific. The grades range from I'll just say for the undergrad, the grades range from missing I forgot exactly what it was, 5 or 6, all the way down missing into the high 20s, I think. But for the most part, so I didn't even consider the graduate grade. There are 3 graduate courses in the adjustment. The adjustment was all having to do with okay. Go through the answers to the test. And one reason why I do this is that if you feel like after having explained to you, if you feel like your answer was correct and was graded wrong, then you have that opportunity to either bring it up right now. You don't care about it being private, or you can bring it up later. Either way. So number one was adding two raster layers together. What type of operation? That was a local operation. Doing an addition between two raster layers. Local operation. What operation identifies the downslope direction? The direction was the key word there of the maximum rate of change in value from each cell to its neighbor. And what type of operation? So that's aspect and focal. And that one was worth 2 points. First one was worth 1 point. Number three. Vector GIS might use buffers to do proximity analysis. For example, find all the areas within 500 meters of each. Describe the process operations to run, in which I could produce a raster data set that has values of 1 in areas that are within 500 meters or feature values of 0 or greater than 500 meters. Diagram if you like. Your explanation may not simply convert a vector buffer. So what I was saying there was it is possible to solve this problem by saying, okay, let's buffer the vectors by 500 meters and then convert that into a raster data set. And that would only be a 2 or 3 step process. However, the method that's easiest in raster is also only a 2 or 3 step process. So you had to do that. The method that I think is easiest, I got full credit for, was to run a Euclidean distance operation first. And after running a Euclidean distance operation, you would have had raster where every cell represents distance from the feature. I didn't specify what it was. Then you could do a conditional operation. People said a map algebra operation where there was a conditional phrase in it. Anyway, whatever you said, you had to do that, or you could do a reclassify. You would have gotten credit for that. 2-step process there. First, you put in distance. Second, to some sort of tool that would have created those ones. All right, so that one was worth. I think I made that one worth 4 points altogether. 2 for identifying those two operations, and then 2 points for identifying the input and output in the analysis. Okay. 4. As discussed in class, in the capability suitability modeling, pass-fail screening uses multiplication to combine these factors. The cells with an unsuitable area for a particular factor would be coded what integer value. And so initially I thought that should be 0. People put no data. No data is not an integer value. But I gave credit for that one. That was worth 1 point. I gave some credit for that. All right. After running the Euclidean distance tool, what do the values in each raster cell represent? Actually, going back to the last one, the reason that 0 is the correct answer, when we're using multiplication, we're trying to say that it's unsuitable, then 0 times anything will equal 0, so it'll be unsuitable in the output value. Okay, after running Euclidean distance tool, what do the values in each raster cell represent? They represent the shortest distance from the center of the cell to the nearest source. That one was worth 2 points. 2 points. Partial credit on that one. Okay. Yeah, go ahead. Yeah, go ahead. The shortest distance to the nearest source was the correct answer. The shortest straight line. The nearest source. All right, six. With a 3x3 focal mean kernel, fill in the gray cell in the output grid. Probably should have made the numbers kind of neater. Anyway, the correct answer was the further north cell, top cell, 5.3 repeating. The lower cell was 6.5 repeating. And I did accept round it off for full credit. Yes, sure. And I was fine. All right. So for the top cell, the one that I said the correct answer was 5.3. We're talking about a mean. So it's the mean of all the cells surrounding that cell, including that cell. So it's the 9 cells that are 3x3 from that center cell. So it's 4 plus 10 plus 5 plus 0 plus 9 plus 3 plus 4 plus 5 plus 8 divided by 9. Alternatively, you could multiply each one by 1/9 and add them all up. That was another method that we talked about. We're doing a mean kernel. It would have produced. It's easier to add them all up. Divided by 9. So same thing with 6.5 repeating. Would be 9 plus 3 plus 5 plus 6 plus 5 plus 8 plus 5 plus 4 plus 10 plus 9. Add them all up and divide by 9. All right. The next one was doing a conditional operation. So this conditional operation, we're still looking at the same 2 cells, but we have a different input grid to start off with. And so with a conditional operation, it's a local function. So we're only looking at cell by cell. We're no longer looking at a window. So we're only looking at the values 8 and 10 in the input grid. And how they fit into this function. So the condition, the input grid, if it's greater than 8, the way we read this is, if the input grid is greater than 8, the value will be 100. If it's not, then it goes into this other condition that says, if it's greater than 5, the value will be 50, else the value will be 0. And so the only possible output values are 50, 100, 100. Since 8 is not greater than 8, it goes into the second true-false statement. So in the second true-false statement, 8 is greater than 5, so the value is 50. That's why the top value is 50. In the second one, 10 is greater than 8, so it gets the true value is 100. All right, using the AND operator. The AND operator is basically a Boolean operator. It is a Boolean operator, as we talked about in the class. Fill in the not grade cells of the output. And so AND requires both values to be true in order for the output value to be true. If both values are false, or if either value is false, in fact, I should just say that. If either value is false, the output will be false. And any non-zero value is considered to be a false value. So 0 and 7, 0 is false, 7 is true. So 0 and 7, the output is 0, false. 7 and 8, or 8 and 7. Those are both true. So the output is true. Those are both. You get 0 for the top one, 1 for the bottom. That's the correct answer there. Number 9. The first layer below is a value range. In fact, this is one that I was surprised more people had. More people didn't get this one correct than I thought. So this is an opportunity to learn what zonal does again. Okay, so the first layer below is the value raster. In other words, it could represent elevation, vegetation, whatever. The second is the zonal layer. It's the one that delineates where the zones are. So what is the zonal sum of zone 3? I should have written out. I should have wrote 3. I don't know. But zone 3 is all those cells that have a value of 3 are zone 3. So the zonal sum is the sum of all of the cells in zone 3, which is the last two on the first row, the second to last one on the second row, and the first one on the third row. First one on the third row is a 0. It doesn't have anything to do with sum, or doesn't affect sum. So it's really 8 plus 5 plus 2, which is 15. Correct answer, 15. What type of operation would I use to find the average precipitation that occurs within a polygon? More people got this right, which is basically the same problem, 9. Much more people got this one right. Assuming I had a raster representing precipitation, and that's zonal. All right. Question 11 through 14. Use the following model types to fill in the blanks. Not every answer will be used, but each answer should be used only once. So I put that in there because there was an answer. They ended up giving like half credit for that was technically correct, but not correct because every answer could be used only once. The number 11, models that have only one outcome for a given set of conditions are deterministic. That's really the only one that fit that one. A digital elevation model is an example of a scale model. It's really the only one that fit that one. Weighted linear combination and capability suitability modeling is modeling using a mathematical approach. Now, technically, deterministic could also fit in there, but you should have already used it in there, number 11. But maybe you use stochastic incorrectly in number 11, so then you use deterministic in 13. You should have gotten half credit. All right, 14. Model builder allows users to build their ideas into graphical models to directly execute. Some people put mathematical, and there are mathematical elements to them. But the thing that you see is an example of a graphical model. Inside there, basically there's a lot of little mathematical models inside of the graphical model. All right. Anyway, those were worth 1 point each, but I did give some partial credit for those. Number 15. In the grid, on the left, below, the value 1 represents forces. After running the Euclidean distance operation using this layer, fill in the non-grade cells out below, assuming a cell size of 100. Those sources are supposed to find in the output grid the shortest distance back to one of those sources. The top grid should be 0. The top cell should be 0 because it's already in a source cell. So the distance back to the cell is 0. The one on the next line, the shortest line back to the cell is diagonal back to that same cell as as before. It should be, you know, I actually gave partial credit for square root 2 and full credit for 100 times the square root 2. Anyway, the answer is 141.1, rounded off. And then finally, on the bottom cell, the closest cell is its neighbor, and its neighbor in X or Y direction, north or south direction. So the distance from the center of that cell to the center of the cell being considered is 100, because that's the cell size. So 0, 100 times the square root 2, 100. One of the correct answers. Number 16. 16 is how does running most local or neighborhood operations affect the spatial autocorrelation of a raster? This was the most question in the test, so it probably wasn't a very good question. I basically assumed what the term spatial autocorrelation means. So Brittany said things that are near are similar. And that's really close. Technically, things are autocorrelated means that things that are nearby are related in their values somehow. Okay, they could actually be inversely related. As you get close to something, the value changes dramatically. In any case, it has to do with term spatial autocorrelation. I wasn't asking you to quantify it or anything. What I was saying is, if you run a neighborhood operation, since you're basically looking at the nearby cells and using those to change the value of the center cell, you're going to increase the spatial autocorrelation. You're going to increase how related nearby cells are to each other. Basically, pretty much no matter what operation you do, unless there's some sort of randomness you're trying to generate based on nearby numbers. Anyway, any function I can think of will cause the nearby cells to become more related. It's inverse or positive or negative correlation with the cell in the center. So, although a lot of people miss that, basically the fact that I adjusted the test scores has the effect of throwing it out. I think one or two people of all the people who took the test answered that one correctly. All right. So that was number 16. Just it increases. All I was looking for was the spatial autocorrelation. Maybe getting you to try to think about that. No, we mentioned it, but we didn't call it spatial autocorrelation or something. In any case, that was a very missed question. 17. What is the difference in the outputs of the zonal statistics tool and the zonal statistics as table? So here, the answer is pretty straightforward. The zonal statistics table produces a new raster where all the values in that raster will be the zonal statistic that you chose. The zonal statistics as table outputs all of the zonal statistics were selected. It outputs the zonal statistics into a table. The answer is almost given in the question, so that was fairly commonly correctly answered. All right, 18. Ordinals are used in what type of operation? The correct answer there is focal or neighborhood operations used. All right, 19. Explain why slope calculations will never result in 90-degree slopes, even if one existed in nature. And so here, the correct answer was that the run will always be the run will always be greater than zero. So we'll never have positive slopes. And the run's always zero because we're considering a cluster of cells. It's a neighborhood operation. You could just say, well, it's a neighborhood operation. Run will never be zero, which is what would be required in order to produce a 90-degree slope. I stopped putting the notes on the notes. Pretty sure that it was only worth one, but it might have been worth two. I'll go back and answer that at the end of that. After our break. All right, number 20. Multiplying a value in one grid by a data value in another grid will produce what value? No data. I know that was good. Number 21. Explain what is different in finding the average slope of a given area versus finding the average surface orientation of the same area using the method outlined in Hodgson and Gale. So here, some people thought that I was talking about asking, but they basically answered this question: what's different in finding the slope versus finding the asymptote? And I did give partial credit for that. This one was worth like 3 points. But because I threw in that method outline in Hodgson and Gale, I expected the actual surface orientation we talked about in the last lecture before the class. Basically, here, average slope would give you simply just the average downslope, the average degree of downslope, the average amount of how much the average amount of change in any direction, just average. Whereas the surface orientation would average both the distance, both the slope and the aspects together to get the average angle or the average position that it was facing. It's drawn like my crude drawing in the diagram. Two slopes going the opposite direction would be average flat, whereas I took the average of those two slopes. So we're both 45 degrees. You can still get 45 degrees. Number 22. In a cost distance model, what are the values? What do the values represent in the cost factor? Okay. If costs are compiled from multiple sources, what sources should they be in? This one was worth at least two. I have my notes here. The cost raster represents the cost to traverse that cell. And the cost, if they're compiled from multiple sources, here it was important to say that they should all be in the same unit. It wasn't really important to actually say that they should be dollars or whatever. So if you just said they should be in dollars, you didn't get full credit. If you said they should all be in the same units, for example, dollars, then you should have gotten. All right, the last one was worth 5 more. Diagram the process of cost distance modeling. You should start with two cost rasters. One represents the land acquisition cost in dollars. The other represents material costs, and also in dollars. We'll have a layer representing sources and a layer representing the destination. Final result should be at least cost. So basically, you were to reproduce this diagram in on the bottom. I made it worth 5 points. So there were lots of partial credit. In order to get full super credit, you should have at least recognized that there would be an operation to combine the two different cost surfaces. I didn't say how they should be combined. Put anything in there, but if you did, that was fine. Cost or friction, those had to be combined. These right here. And then the cost distance algorithm reducing the cost distance and cost direction and the destination in here. You get the least cost path algorithm, and finally the least cost. Okay. And again, there were some adjustments to the grades, which I got on the term grade online. The grade that I assigned for the class. And if you want, actually, I'll just put it up on Canvas eventually, because there were higher C's and lower C's. You want to know the exact percentage calculate your grade. I'll put that up. Yeah, I figured out how to do it. Before basically I found out how to have two different grades. That way it won't. Okay, so are there any questions at this point? Any general questions? Like I said, if you want to talk to me individually about your grade, that's fine. And if you want to ask me questions, Well, the slope is calculated as the rise. And since we're using cell size, the run is always actually going to be 2 times. Like in the formula. The module. Going back here. Okay. So the rise is all this number. The run, change in the x and the y dimensions is always going to be a number. As long as it's a number, you're never going to get a 0 run, which is what's required for a 90-degree slope. A 90-degree slope would be like so 45-degree slope like this. 50-degree slope is a little bit more, 60, 70, 80, 90, straight up and down. In fact, if you divide anything by 0, what do you get? It's actually undefined. So the tangent of a rise over 1 0 is actually defined as undefined. Tangent of 90 degrees is undefined. So the inverse is 90 degrees. You can get really close, like as these numbers get bigger and bigger, higher and higher, If this cell here had a value of 0, this had a value of 0, and this had a value of like 700, it would be an almost 90 degree slope. It wouldn't quite be like 89.8997, whatever. Well, you can't have it. 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 So that's why never get a raster. There's no such thing as if you ask ArcGIS or any other program to calculate slope this way, you'll never get a 90 because you're dealing with calculating slope over area where you're basically saying, okay, what's the slope for this area? As soon as you start saying what's the slope for this area, you find it as having a run. You're looking at different points in space. And never be 90. You'd have to be looking at the same point. Because it's a neighborhood operation. That it'll never be 90. 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 All right. So the second thing that I said is just kind of finish off, or provide a few more. We did a little bit more of this up here, and I made an announcement on the canvas. I just want to make sure. We spend 15 minutes or so talking about finishing up labs. So we need to calculate the zonal mean. In fact, basically, we're doing what I was picturing. We were doing question 21. I don't even think I have that up. So I gotta bring it up. I gotta add lab. Lab 6. I gotta download it. Well, I'm sure I have it. The toolbox. So one of the things that I said there was, let's not worry about calculating the aspect part of the equation. Just calculating the slope for the lab. Is this the right lab? Is that the right lab? Yes. But it's the surface normal. Right. I'm just going to copy this whole thing out of the directory. And maybe it's out there. I forgot that it was called terrain. Oh, that's not where it was. That's fine. Okay. So I'm going to add it in there. Add toolbox. Terrain. So the result of this tool produces those three topographic normal vectors. They're right here. X grid, Y grid, and Z grid. And so the assignment, one of the assignments, one that people are having is I need to take these three values and plug them into the formula that's given in the text, which I should also bring up. Which is this formula right here. Actually, it's better, and it is better. Ooh. So in class, I just said, okay, go to it. Okay. This is what you need. So how do you X sound, the Y sound, the Z sound? How do we get them? Right, zonal statistics, easiest to do zonal statistics equal. You do it that way. We also do it as regular zonal sums. Point up with raster relay. You could do, and then you could put this in the raster out. But the way that I went over, just use zonal statistics equal. You get this one. Then join them together a field calculator expression, which that's what I was alluding to that I put into I put it as an announcement, right? That's where I put it. Some people have found it. Field calculator. That's assignment. Yep. This is the calculator. So, looks like Adam asked a question. That's fine. We'll just go ahead and do this real quick. So, what I'm going to do is add on those zonal statistics, those tables, to the end of this model. That's under spatial. Zonal statistics as tables. You could do this as a separate model. Then I'll just link these guys up. And then go into here. I'm gonna go like this. I'm gonna say make variable from parameter zone feature or zone data. And we actually have those zone fields. We know the zone data that I have to use, which is in the called zone. I'm going to feed each one of these with the same zone data. And then finally, I have to change the zone field. What's the zone field? That's the only one on. But the zone field will tell you the field is going to be the output, the identify. Zone 1 will have this. What does this drop down to? Right. Right, leave that as all, anything to even, but we don't really need all of them. Some. So let's just change it to some so that we just get that way. Changed each of these to some. All right, I'm gonna save this. I'm going to change all these to model parameters so that I can save them out. I can save them out to a place that I specify. Close this down. I'm going to add in the elevation data set that I'm working with. Then I'm going to run this. So I'm going to choose not that one. This one. I'm going to choose the cache data. That's where it's going to put everything in those ones by default. I'm going to rename these so that it's more convenient. Z grid. X grid. Y grid. I'm gonna call these guys. I should have named these. Fact. I gotta name them so that I know which one's which. This one comes from the Y. So rename that one. Zonal Y. This one comes from the X. Zonal X. And then finally zonal Z. I messed up. I should have renamed the output. Put it Z sum. For zonal sums. No, X. So basically what I'm saying here are those three outputs. And the reason that I'm doing that is so that when I go to here, I get names that make sense. Otherwise, I wouldn't have known which one to go. Really gotta figure out error message. So these are really the only ones we care about right now. Z sum, X, and Z sum. Okay. So I'm going to run through. I'm not going to save those other things right now as files that I want to use. So when this runs through, I'll have three. What will those? Z sum y, Z sum x, Z sum z. What will those be? Type of data set. Tables. Exactly. There'll be tables. With those tables, I can calculate the function using this function category. If I open these All right. How do I get all these tables into the same table that I can do a table join? What do I join? When I join, I have to have a column to join on. Which field do I join on? Yeah, the ID. Why do I use the IDs? That's what I use with Adam and hanging down there. That's what I use to create these zones. So zone 0 is the same in all three. Zone 1 is the same in all three. Zone 2 is the same in all three. If I combine them, I'll have normal sum, x and y in the same data set. Now, they're all right now. They're all named the same thing. They all say sum. So might be easiest. You can't rename a field. It might be easiest to just add a new field. And this part you don't need to do a model builder. As long as your model does what your model did, it'll work. You can change this to float or double just because the numbers are doubles. And I'm going to say y sum. And then I'm going to just calculate the sum as the y sum. So now, you join all the tables, you don't have to remember which field was which. They're going to be called y sum. If you want.
How bad or deal with my numbers, right? They're very close.
The y sum values.
Everything's relatively close.
Well, if it's no more than 8, it's not a big deal because we're going to feed these into other equations. So, I mean, it's a little puzzling that they're off by such a small amount, but it's not a problem. Sounds more like a. Yeah, maybe. Now the only difference is that you did the zone statistics as a table. I mean the other part of what I'm trying to say is I made all this part. So the only difference should be here. Right?
I did my
Right. Yeah, no, that wasn't my point. If you put it in a separate model, that's fine, but it's still used as inputs to the degree that you calculated from my mob. Yeah, so really, this has the only chance of being different. I'm not exactly sure why. It would be different, but it's okay. I mean, like I said, since we're going to be putting those into the trig equations, off by that little major differences. We can verify that. I'm just doing this for convenience. I'm going to delete the original sum now, so that I don't see that when I do the join. I'm going to do the same thing for each of these. Create a new field, maybe a double, maybe called X and I'm going to calculate. And then I'm going to remove it. All right, now I'm just going to go through the process of joining them. I'm going to join this table to z sum y, and I'm going to do it based on the ID field. Now I have z sum and the y sum in the same table, and then do one more join. Join the x, and I'll have a field using the ID and the ID. Now I have each one of those. Now the last thing I have to do is to add a field called It's the slope. I'm just going to call it z slope for the slope that we're going to find, the average slope in that area. But accounting for its direction as well as the steepness of the slope itself. I'm going to make this a double as well. And then, why does it already have values? All right, so now I have to put that formula in here. I'm going to select Python, and then copy that formula in there. The only thing I need to do is change these field numbers to the correct field. Unfortunately, the field names are kind of cut off. Oh, if I hover over. Okay, that's the z sum. I need to find the x sum. Looks like it's right here. Here we go. I'll do that again for the x. And the y. And the y, and finally the z. Then what's the right. Yep, exactly. And then I do the radians, Let's see, which one would I need? From radians? It's radians 2 degrees. So I need to multiply it by that value. Whole formula is going to produce a value, A produce a value and you multiply by that to get degrees. So say okay. It failed. How did it fail? Second. There's something weird about this field. Why does it say values already? Okay. Now look, why is my X on blank? That's probably why I'm having a problem. All right. What I'm gonna do? Double. I'm gonna get rid of this. Because that field doesn't going out well. Working. There's something wrong. Now I'm going to join back the ID. I mean, join back the Y sum. Okay, so now I have them all three in the same table. And I'm going to join them each individually. ID. Okay. And then I'm going to calculate this value. So I'm pulling the value out of the other table. And then I'm going to remove that join, and then add the X in, the X join back in. Okay. Okay, so now I have to change these out. That'll just be plain old X Y and Z. Make sure that says Python. I don't know why that's. Anybody get it? Has anybody gotten it? In a model. Did you type the buttons here? Yeah, I got this worked last year too. Everybody see what I'm doing wrong? QRT. I'm trying to use these numbers. All the columns. There's something wrong because, like, even if I type in 1, I was getting there. That was working. So look, even when I just type in that, I get in. Maybe that's it. See, that's. What if I just have one of these numbers? There's something amiss, but I can't figure out what it is. Oh, I do. 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 Well, I'm trying to make it smaller. I'm trying to make it smaller to see if I can figure out what's wrong. This one. 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 Okay, so that should be right. 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 Math.8.SQRT. And that should be. Okay, are those the numbers that you got? Is the square root just the numerator? It is, Yeah, I have the square of the whole thing, right? Square root of the whole thing. 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 Like that, like that, like that, like that. It should do multiplication That didn't change. Let me look at the formula here real quick. It looks like it's just over the top though, right? Just over the top, the root. Yep. So one of these guys. Yep. Are those values? Those are you guys? Okay. It's just like a matter of getting right. I did this last week. It took a while to get it again. I don't know why. The thing that I did. Unnecessary step. It made it good sense in my mind. Anyway, good work. Is there an extra exclamation point? Yeah, there's an exclamation point right there. Is that in there? Is that in the announcement? Yeah, so that was a mess up. That was the problem. That was the extra. Sorry about that. Okay, so once you get that, you'll have the answer. Has the highest slope. Highest average slope. So let's look at that. Where's zone 2? That was the right place. So that zone right there. Now, look what happens if we go zone statistics table, and we choose zone, and the value raster is going to be the slope. Okay. done running, 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 done running. Nope, still running. Nope, still running. Nope, still running. There it goes. Okay, okay. So there's the. So let's look at zone 2's value here. Well, that is the average slope right there. The mean 32. I'm gonna run that again. I'm just rerunning that. If by default it only runs on the highlighted. But zone 2 there, its mean slope was 32. Doing it just by taking the average slope value.
Still the one with the highest. Why is that value 32? Another time it's 17. Both average slope, looking at slope differently.
And that one in particular, the one reason why it goes down.
Got a lot of slopes this way. Different average value. When you just take all of the higher value, all of these slopes are pretty steep going in different directions. But the lower value, instead of all the directions, average. Overall, they're not that much.
Is the value when you just consider the surface orientation itself. The average surface orientation of that area has a slope of 17. The average slope on a cell-by-cell basis is 32 degrees. 2.6. All right. So that was. Go ahead. The average surface orientation has a slope of 17. Okay. All right. We've gone on for a pretty long time. Let's still do the lecture part, and then we'll do the lab. Okay. So that is in modules and 7. All right, so sorry I didn't get the reading earlier. But the reading is oldest reading that you'll do, but this is still how the hydromodeling tool runs in our GIS. So it's analyzed. I mean, it's basically the article that usually describes how that done.
We talked earlier about a little bit about today we're going to look at these slope area,
We're going to talk about how we can model those values. Sometimes this is referred to as hydrologic modeling. Useful in many fields of study, digital elevation model basically a scale model. We actually have real tangible digital elevation model. We poured water on it.
hopefully that water would flow off of that model, similar to how poured it on rain, put it onto an actual model or an actual now. The actual surface of the earth is pretty complicated. There's different oil types, vegetation types, land cover types. Sometimes the water soaks in a little bit, sometimes it soaks in a little bit less. Still, one of the primary inputs to hydrological modeling is shape of the earth. So how shape of the earth and the other parameters affect water flow. We want to model. What happens when a resident good to build a residential land cover of that area. How's it going to affect runoff of water on that watershed? How can these changes be mitigated? What can we do to change it? And if we do make a little change, what's that effect going to be? It'd be nice if we could actually model. So that's why these scientists that came up with the methods for modeling rainfall runoff. That's why they were doing. Come up with a way to model how water comes off the earth. So that why do we need a model? Well, the model will help us to come up with good practices for land use and development. So oftentimes hydrologic modeling involves a digital elevation model, but also we can include other parameters that help us to determine the amount of runoff on a cell by cell. There's like a three-dimensional rendering area. There's same data, but we've got a map draped over that area. So if you can imagine this kind of contour map, we actually had to do this back when I took First thing that they did was ask us, okay, this is find all the area that is going to flow into that area. The way that's done is follow perpendicular all the way up to the ridge line. You actually draw that. So we did that as an exercise. It looks kind of like that. That's the watershed on perpendicular contour line across the ridge line. That watershed, all the areas, that out. That's one thing that the people did even before GIS systems. Draw watershed boundaries. One of the replicate this in a GIS system. All right. The other thing that we're trying to replicate, we're trying to do, is to come up with a drainage system on which the waterfall, and not only that, through which it travels to an outlet. So if you look at this slide, water goes the water flows down here to another stream. At the outlet that we've chosen. So we want to be able to model stream now. We want to be able to determine what that drainage referred to as a watershed, reading area, whatever you call it, based on an outlet point,
in the area above the outlet point. A subbasin is an upstream area flowing into an outlet as overland flow. The subbasin is part of the basin. It may not actually have a stream inside it. It might be flowing as overland flow. The point is that what it defines this whole basin area referred to as a core point is the location from which a contributing area is determined. The drainage divide is the other end. It's a boundary, so it's a linear feature. A boundary between two basins, the area where flow is diverging, going in opposite directions. All right, so this paper that you should go back and look at seeks to basically create these features in a raster using a raster grid of elevation. So considering a raster grid elevation, we're going to create these same sort of attachments, core points, subbasins, drainage networks, using as input a raster GIS. Talk about this elevation. That's what we're talking. I often find that it's helpful actually display a digital elevation and then make the digital elevation partially transparent. She's really fun. Helps you to see what's going on in terms of where water's flowing. Okay, so let's get in. My thing kind of a direct progression. We talked about last week, calculating slope and aspect. Next step beyond that, calculating slope and aspect might be calculating a water flow. Calculate slope, and feed that into the model. It's still a local operation. We're not going directly from calculating slope. Hydrologic model. Hydrologic model still works on cell-by-cell basis, and still attempts to operate on a focal area, a 3x3 cell area. But it looks based on slope, actually the greatest drop. We look at all of the all of the slopes from the center cell to each of its neighbors. It's not like we're calculating one slope value. Sorry, 9. Calculating 8 different slope values. Calculating 8 different slope values. And it's finding the one that is the direction of slope. Into the target. So what's the slope here? What's the between these two cells? What's the run? Run is the cell size. Going center cell. For the run there, just call it y. Rise is 0. 0 over y. Figure out what the angle of that is. The slope there is 0. So X that one out. All right, going this way, and to 1. So the run is run, and it rises, right? Slope is
5, but is a positive or negative? Well, one or the other. It's not the good one, right? Good one, right? 10 to 13, well, uphill too. All these are uphill, except for these two. We need to figure out which one has the greatest slope. Which one's it gonna be? It's gonna be 8. Yeah, that one has the greatest slope. The way this algorithm works is that water is said to flow this way, from this cell into that cell, that direction. And actually, the only thing that you have to really think about is that the slope that's calculated from the center of the cell to this cell still uses the actual distance between the cell center. So this would not be 1, it would be 1 times the square root of 1.41. However, this is the same distance, so we know this is a later drop. There are several directions, several algorithms used for calculating the local drainage direction. The one that I mentioned is the one that's implemented in our GHY. It's called the D stands for deterministic. In other words, given the same set of outputs, always have the same output. And water is said to flow into one and only one cell. The flow direction is in only one direction. Simple rise over rise. Cell size, or cell size times the square root of 2 for diagonal. Okay. So the first step in this implementation is called calculating flow direction. So if you go back over to this guy, I'm going to delete everything except for the elevation. Delete these guys too. All right, so if we go to hydrology modeling, the first step here, we're talking about now, we're actually going to put some other ones before it, is this flow direction. You can input your data set, and then hit OK. Turn the zone, I forgot to turn the zones on. Okay, so there's the output of the flow direction raster right there. And if we look, I'm going to symbolize these as unique values. I am Y. Sorry. No. You have to. I guess I have to escape from here. There we go. I'm gonna say unique value. So those are all the unique values. 1, 2, 3, 4, 6, 8, 10, 12. We'll talk about what all those mean. Really, there's really 8 directions. We get all these different values. Go back to here. Generating flow direction. Output brings values in 255. Based on the direction of water flow, how much particular cell. So, if it only flows one of the 8 directions, it comes as these values. Flows to the west, the value of y. Actually highlighted it now. Most of the west, most of the southwest, outward. 28. Here's where I'd ask. Why is it using these numbers? Didn't have to read. I'll just go ahead and explain why it's. If there are two slopes are equally great, you can add up these numbers. Always. Every combination numbers. Always unique. 1 plus a 2 is a 3. Obviously. Oh, they're 3. Really, 4 plus an 8. What? 12. So a value of 12 in the output grid, these two equal. Value of these two are equal. Even 8 plus 4 plus 2 is 14. Isn't the same as 6. Any additive combination. By the way, what are these numbers? Powers of 2. Powers of 2. That works.
So they're assigned a value. So if we go back over here, we've got some 3s, 4, 6, 8, 10, all the way up to 12. So what's 12? Probably 128 plus. Anyway, we could find out what it meant, but it means that flow is in a certain direction and more than one direction. So here in this example, the reason that it would get a value of 4 is
here it doesn't. Let's just say this wouldn't really matter what it is. In that direction. Be the highest.
So 4 meaning that it's flowing south. So that's how that was. All right. So this is from the reading.
Code them as 1, 2, 4, 7. And we can resolve that. ArcGIS actually has a method for resolving these cases, but flow direction math known as a combination.
All of those values. So we could recode those values that we saw as east, southwest. All right.
There is another problem though with processing digital elevations, doing hydrologic modeling. The first problem is that sometimes there's error. Even without errors. Digital elevation models often contain things that are called. These might get created because digital. Let's say the digital elevation model is based on LiDAR data. And anybody's ever walked on a railroad track? Railroad tracks higher than all the surrounding area. But every once in a while, railroad track, there's either a culvert or a bridge or something that would allow water to pass underneath. But if we used a LiDAR instrument to create visual elevation model, would a culvert really show up? Culvert wouldn't show up. So it would There would be no way for water to pass through. We might refer to that as meaning that water should be able to pass there, but it doesn't. And sometimes these can create, in other words, areas where there's no flow direction out of that area. Because everything falls into a certain place. In reality, there's a culvert there that allows water to leave. Doesn't just pool. Even if the water did pool up, what happens eventually in a low area? If it fills up, what will happen eventually? It'll spill over. Go somewhere. This is one way to model or to fix those errors and to model that filling up. Basically, what you can do is you can say, okay, where would the water flow if all of the sinks were already full? Where would it continue? So, that is right here called fill. So fills sinks in a surface raster to remove small perfections in data. So if we put Shasta in here, we say okay, then it's going to produce a new DEF that doesn't have any sinks. It has to do this iteratively. It did it pretty fast on this data, but this is an intensive process. It takes a little while, a bigger, more detailed. I wonder if I created data. This is not the data for this lab. I wonder if the sinks have already been filled. Let's see. What I'm going to do is see if there are any differences. Subtracted the filled data set. There are. Okay. So these areas are sinks. If we can look at those real quick. I just did the hill shape. So this area right here is a sink. That's probably. All the water the way that I figured out that was a sink was I had ArcGIS fill the sink, and then subtracted it from the original. Basically calculating direction. Every time it finds an area where everything's going in, it releases that area and does it again. All full, until it's out of that. It's an cycle. Why it does take. You can specify as part of the that you do not want it to go up, fill it up until they don't give up, that's filling sinks. So if you want your data to create a drainage network, this is actually the first. So it's an optional step. Fill sinks fill is what's called first. Then the flow direction is next. These are actual value. We were to try to model water flowing away from this raster, go, five, then it would have flowed. All of these are higher. This is a sink. This whole area because of that cell. So fill sinks always raises to match that value. All right. Operations oh, fill. The reason it has to be iterative, like the way I describe, is sometimes filling actually creates. So this is the actual algorithm or process that ArcGIS does in order to fill things. Each cell's elevation, the lowest elevation, raises everything up. And it competes flow direct. And it looks for things again, goes all the way around. All right, the next process, model water flow, referred to as flow accumulation. Flow accumulation is it produces a raster where the value in the raster represents the number of cells that are upslope of that cell. So if it has a value of 5, it means that 5 cells flow into that cell. So it requires the flow direction. Flow direction is one of the inputs. By tracing backward up the flow direction grid, the computer does that. It goes backwards up the flow direction grid for every cell. It goes cell by cell. For every cell, it traces back up the flow direction grid and calculates all of the cells that are upslope of that area. And so it's a measure of the accumulated flow. Represents, I've already said number of cells. You can wait, give it a weight raster. You can weight some cells more than others. This is useful if you want to actually model runoff. What you can do is say all of the paved over areas have a higher value than the non-paved over areas. It's very simple. It's a simplification. You give a weight of 100 to all the paved over areas, and 50 to all the non-paved over areas. And then your flow accumulation will be based on that weight. So every time it saw a non-paved over cell in the upstream, it would add 100. A non-paved over cell, it would add 50. But one of the useful things that this does is allows us to start to model where stream channels would fall. Because stream channels are places where there's more flow accumulation. But this is a areas where flow accumulation is the highest. those are the candidates for areas where stream channels will form. I mean, there's different things that go into whether or not a stream channel actually forms there, or whether it's dry sometimes, wet other times. But these are the places where stream channels will likely form, or are likely already in existence. This is related to flow accumulation. This graph shows the flow length. Flow length is the distance. Here's the pour point following the flow direction. So it's kind of like a distance. The number is a distance. The number in the flow length graph is a distance along the path out to the flow point. This is useful modeling how much water will get to which place. If a watershed really steep, has very short flow length, a lot of water rushes out. Here you'd have to plan for having a lot of water. If the watershed's fairly flat and has kind of like that watershed back on the first slide, hot dog shape, then you'll have the water that flows out of there will flow more evenly out, because the flow length and the slopes are both shallow. In reality though, we actually tend to get long, thin, but steep slopes, like mountains, at long, thin watershed, very steep, or very flat, wide. Those are really common shapes for watersheds, but they have a different characteristic of how much water gets to a certain point at a certain time. So this is the whole elevation yeah. I mean, this would work in practice. Flow direction. Just fill the sinks. Fill the sinks. And right beforehand, and then stay on it. Nowadays, computationally, it is a hard process. They only take. Fill the sinks, then do the flow direction. Then calculate watershed, calculate accumulation, calculate the flow path. Look at this flow diagram. Don't calculate watershed, we'll actually calculate accumulation. Almost everything is built off flow direction. Watersheds built off flow direction. Accumulation. Flow length is built off flow direction. They're not like things that you have to do. Calculate flow direction. You calculate most of these other things. Here, these are the different processes off of flow direction.
Watersheds, streams, flow paths, those are all different processes off of flow direction. Okay. This is really just doing the same thing that we've already talked about, getting into a little bit,
actually showing the numbers. We're going to do this actually do it by hand, for a hand, helpful. Here on the test. Yeah, this time, have actually some by hand. The connection between lower and better. Anyway, here with elevation, flow direction. Every cell, cell by cell, calculating flow direction. That's what these directions water is flowing out of everything. Look at this. Determine if there are any sinks. It does not look like sinks and that.
Technically, if I go back up here, anyway, there's no sinks in that data set that I can identify. In the lab one, there will be.
The basic direction. Where the water is flowing, behind.
And that is what's used to create flow accumulation. So this is the number of
What you could do with the flow accumulation is say, okay, value over 7, use conditional state. Value over 7, we're going to call it a 7 or greater. We're going to call it a stream. We can make where all the stream. Anything that's 0, that's the watershed boundary.
So calculate that. This is an old ARC view diagram showing that. Flow accumulation. All right. Okay, so we've basically gone over most of this. I did use it.
Point is something that unify 4 point input. So in order to calculate watershed or stream area, do a 4 point flow direction.
You can break. Sorry, go ahead. I was going to say you can break up a watershed. That's what this tool right here is called. That's what this tool right here does. That tool doesn't appear. There used to be a catchment basin. Well, this seems a little bit different. Anyway, there used to be a catchment. Anyway. slide for now, but you used to be able to say, okay, I know water, divided up, X number of cells, these objects, those for you, and code them. I'll see if I can find out. All right, this is another thing that we're learning these days. Way, start modeling runoff. Once you've calculated those other inputs, using flow direction, easy to compute, mass balance, in terms of F and E. So we can model the runoff as the surplus of water per cell by cell basis. The runoff is a function of how much precipitation got, how much infiltration occurs. Now some of it's going to go into the soil, and then some of it's going to evaporate. So what we can do, we can actually model the amount of water that's going to turn off in the watershed. You could come up with a way to model evaporation. Then we'll have a value, runoff value by cell. That cell by cell flow accumulation model. Find out using flow accumulation, weighted flow accumulation. Come up with total amount of runoff per watershed. That's as far as we're going to take it. See how then we can say divide watershed by flow length. Say okay, this is how much it's going to reach at this at this point. In other words, looking at it on an hourly basis. Maybe I'll demonstrate. That could be like a. That would just be one more step. Cumulative flow of the network. Or the flow direction. All right. Sorry, do you still have a question? Okay. That is the length of I'm going to calculate flow length here. That's not going to look. Oh, I didn't input the flow direction. I put in the Okay, so this is the flow raster. And you can see one with the same here. Black. But the flow length is the distance from that cell, either upstream or downstream to either the pour point or to the top of the watershed. So basically, kind of like Euclidean distance, you're measuring, like if you were a drop of water, how far would you have to travel the end of that watershed? Or if you are at the pour point and you want to see back up as far as you could, then that would be the length. calculates the upstream and downstream distance or weighted distance. You could weight different land cover types, but if you don't specify, every cell is just weighted in terms of distance. Now, one thing to note is it's the length of the longest flow class.
That's a little bit more. Swimming upstream, it's not very furthest, not the closest. So also likewise, at a location. That makes, that's always one. Your upstream, you're talking about the downstream to the 4 point, only one out. Only one way out. Especially using the one way out, so it won't matter.
So this time we use downstream. So that's why the
highest value, furthest way from wherever it's flowing out.
Okay. So if you wanted one watershed,
let's say I'm the water right here. Wanted to get just watershed flow length. So if I wanted that value. I would have to mask out all of the other data. That one to be. Because right now it's just go down, falling off there.
Okay. Let's go ahead and take our break right now, and then we'll get into the lab. The lab has a portion that we're going to do. That doesn't even involve the computer, and I'm going to just briefly introduce that. The lab also, as you use a tool that allows you, it's a really cool tool that basically allows you to manually bring it in. Since we haven't used that before, I'm going to demonstrate that. And then we'll talk about the second part of the lab is going to be. So I'm going to go ahead and